Okay, so here we have an Excel spreadsheet, and I'm going to use it for one of its intended purposes, which is to generate sequences. Actually, for this particular demonstration, I'm going to generate the Fibonacci sequence. So a Fibonacci sequence usually begins with 0. That's kind of just standard, but it may begin with any single number, decimal, integer, whatever. But a Fibonacci sequence is made by summing two consecutive terms to create the next term. So in this case, summing term 1 and 2, which I'm going to set as 1 just for argument's sake, to generate the third term. So this is going to be simply the sum of A1 plus A2. Big surprise, 0 plus 1 is 1. If I now drag this down, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5. So it's generating our familiar Fibonacci sequence. Let's just go down a little bit. Let's go down to 20. Okay, let's zoom out a little bit so I can see that. Now, that's not interesting. I mean, what I can do is I can change my seed value, A1 to 1, or I can change it to 5. I can change the second one to -3. We get varying different Fibonacci sequences. Okay, let's go back to our original, the one that we should all be familiar with. And what I'm now going to do is I'm going to find the ratio of consecutive terms. I'm not going to find the ratio of the second to the first because I'm dividing by 0. But I am going to find the ratio of the third to the second, i.e. The third term divided by the second term. That's going to be equal to 1 in this case, divided by 1, predictably 1. Then 2 over 1 is 2, 3 over 2 is 1.5, 5 over 3 is 1.6 recurring, or in this case rounded, 8 over 5, 1.6, nothing exciting yet, but you'll start to notice that actually 1.6 is common, 1.61, and it's actually settling down. If I continue to drag this down, let's go all the way down to our 20, you'll notice that the last 3 terms have settled down to 1.618034, a number which you may be familiar with. It's actually called phi, or the golden ratio. Okay, so basically what we're saying is the successive terms, ratio of terms in the Fibonacci sequence settles down to phi, the golden ratio. But does it actually matter what our 2 seed numbers are? So let's just try 2. And once again, 1.618034. Let's try 1,000. Okay, so it's settling down very, very quickly. Let's try a negative number here. No change. Okay, the first few are fairly transient, and then it settles down to 1.618034. What I'm going to do now is I'm going to convert this into a scatter graph. Okay, well, actually we're going to connect it with lines. So you'll see that it settles down rapidly. So depending upon what I use up here, so let's go back to 0, you can see it settles down less rapidly. 0.5, you can even use decimals. Okay, negative 1.5. Okay, so you'll notice things aren't actually changing very much. Let's put a million in there. Okay, so once again it jumps very, very quickly to 1.618034. So it settles down very, very quickly every single time, regardless of my first 2 seed values. So there's a bit of a curiosity of the Fibonacci sequence that we have the golden ratio up here. Okay, so let's go and do something else with it. So here's a geometric scenario where something strange happens with phi, or the golden ratio. What I'm going to do is I'm going to start by drawing a square. I can change the side length of that square. I'm just going to set it arbitrarily to whatever that is. Then I'm going to bisect AB. E is the midpoint of AB. And I'm going to draw a line to the top left vertex D. So we have a length ED, and that's going to form the radius of an arc centered at E. So I can effectively draw a circle, all the way around, but I'm just going to cross the arc so that it crosses a line which is parallel to AB, the side length, the dashed line, and that's going to form the vertex of a rectangle. So we now have a blue-purple rectangle, and it has side length CF, which is 11.75, etc., centimeters, and our original square side length CB. Now, if I find the ratio of those two lengths, longest to shortest, or longer to shorter, we ended up with a ratio of 1.61803, which should look familiar. Okay, let's do something else now. So we now have a line AB, and the point A is the origin, or rather length 0 to 10, so it's 10 units, and we have point C, which is the midpoint. Now we can move the point C around, which splits the line AB in various ratios. Okay, so we have a ratio of 3 to 7, or 7 to 3, or thereabouts. And I can move my line around, I can stretch my line, okay, but what I'm interested in is the ratio of the whole length AB to the longer length AC, in this case, and the ratio of the length AC, the longer length, to the short length, BC. So we can actually calculate those ratios. So the ratio in this case of AB, or rather the fraction, so in this case it will be, let's go back down to 10, shall we? Just so we've got nice numbers. So we now got 10 divided by 6.6-ish. We end up with 1.5. And then the ratio of AC, which is 6.6, roughly, to 3.4, we end up with 1.967, etc. Now what I care about is at what point on the line do they become equal to one another. So I can slide this up and down. Now if I can get those ratios very, very, very close, so I can see they're getting closer. So that's as close as I can get. And if I go off of that sweet spot, okay, so we want it to go red. I've got a little tolerance set there. And you'll notice that they're around 1.618, rounded to 3 decimal places. Once again, a slightly spooky occurrence, because that's our golden ratio. And I'm going to prove to you that the golden ratio is in fact the exact ratio of AB to AC being equal to AC to BC, algebraically. Okay, here we go. Okay, so what I now have is the length AB, the length of string or the line, is now just 1 unit in length. It's arbitrary, but 1 just makes the calculations a little easier. I've placed C in a completely arbitrary point between A and B, and the longer length, which is the AC length, I'm going to call X, and I'm going to call the other length CB or BC 1 minus X, because obviously it's X less than the length 1. Now what I care about is the length of the whole line AB, which is 1, that's why it simplifies things, divided by the longer length, which is X. I want to equate that to the longer length X divided by the short length 1 minus X. And we formed an equation. You might notice that it's a quadratic when I multiply both sides out. So 1 minus X multiplied through on the left, and then multiplied by X on the right, I get 1 minus X equals X squared, or X squared plus X minus 1 equals 0. So we have a quadratic with coefficients 1, 1, and negative 1. So I want to find out the value of X, because ultimately I want to work out the ratio 1 minus X, which would also become equal to X over 1 minus X based upon the quadratic I've just formed. And we want to figure out what that is equal to. Okay, so using the quadratic formula, minus b, negative 1, plus or minus, but I'm just going to use the positive value, over the square root of b squared, which is 1 minus 4 times 1 times negative 1, so I'm adding 4 all over 2a. So I end up with negative 1 plus root 5 over 2. So what I care about is the 1 over x value. okay, i.e. the reciprocal of what we've just worked out. So that's going to be equal to the reciprocal being 2 over, I'm going to swap this around, root 5 minus 1. And I'd be tempted to find the rationalized version of that. So I'm going to times top and bottom by root 5 plus 1 over root 5 plus 1. And I end up with 2 root 5 plus 1 in brackets over becomes 5 subtract 1, which is 4, simplifies to root 5, whoops, let's try that one more time, simplifies to root 5 plus 1 over 2. So, you are wondering what that is as a decimal. Well, surprisingly, or not surprisingly, it turns out to be 1.618 to 3 decimal places. Once again, it's our mystery guessed phi, the golden ratio. So, looking at our previous calculation, let's just zoom in on our solution, root 5 plus 1 over 2, and remember the other solution was root 5 minus 1 over 2. We only considered the positive value. Now, if we move on to the next slide, there is actually an nth term relation for the Fibonacci sequence. And spookily, here's our root 5 plus 1 over 2, or rather 1 plus root 5 over 2, and here is the opposite, the negative value. And it actually appears, our solutions appear in the nth term for Fibonacci. Now, this is something I've not derived, it's something I've looked up, but let's just see if it works. And we're going to set n equals 1 to work out our first term. So, f of 1 is equal to 1 over root 5 multiplied by, square brackets I'm going to put, 1 plus root 5 all over 2 to the 1 minus 1 minus root 5 over 2 to the 1. And obviously those two are just going to be equal to 1 plus root 5 over 2 minus 1 minus root 5 over 2. I'm not going to do any more powers than that because it's going to get very, very messy. So that's going to be 1 plus root 5 minus 1 plus root 5. There's the top of the fraction, the numerator, all over 2. And obviously our 1's cancel, and I end up with 2 root 5 upon 2 on 2, so that's the, and then obviously multiplied by root 5 underneath, and clearly that's equal to 1. That's our first term of our Fibonacci sequence. Actually, I defined it as 0, but it's our first usable non-zero term. Okay, so what I'm now going to do is I'm going to plug the Fibonacci term formula into the Excel spreadsheet back where we started and see what happens. So here we are back in Excel, full circle, and my first column is going to be my value of n, so starting with 1, moving down to 2, using Excel's autofill feature, I can go down to my first 20 values of n, and my second column, my B column, is going to be my Fibonacci values generated from the nth term rule, which is quite ugly to look at when you put it in Excel, lots of brackets. This is the third attempt, and I finally got the brackets in the right place. So it gives us our first value 1 as predicted by my calculation. If I drag it down, my second Fibonacci value is also 1. I'm going to continue dragging it down, 2. And we now generate our Fibonacci values from our nth term. And I find it curious, right back to what we did earlier, finding the ratio of consecutive Fibonacci numbers converges to the golden ratio, 1.618. And the fact that our solution to the quadratic we solved recently was 1 plus root 5 over 2, and the other solution being 1 minus root 5 over 2 is even spookier. So I've hoped you enjoyed the Fibonacci journey, and here's some nice pictures of some Fibonacci in action.